Welcome to absolute value equations and inequalities. I have the steps above here in terms of solving absolute value equations and inequalities. This is something you have done before in the past. What I want to do is do maybe a little bit more explaining as to why it works the way it does. So before we actually get to the steps there, let's just look at kind of example one I have the three different types that we're going to be looking at. So first one, absolute value of x is equal to 5. Well, we know the absolute value is a distance from 0, and there's two distances that will always give you that positive number, one from the negative side and one from the positive side. So there's two distances that will give you 5, x being negative 5 and x being 5. So on the first one, understanding that just absolute value is a distance, there's two values of x that will provide that answer for you. So we know x is equal to negative 5 and 5. Alright. On the second one, once we get into these inequalities, think about this. What values of x can you plug in that are going to be greater than or equal to 5 when you take the absolute value? Well, just to kind of start off, we know 5 is going to work. Then we know 6, 7, 8, and so on. And that will continue to go on. But you can also go to the other side and say, well, the same thing could happen at negative 5. I'm going to move this to this side. So we could say negative 5 would be a solution, but also negative 6, because once you take the absolute value is 6, negative 7, and so on. So you have these two different sides, in terms of a number line that you're getting solutions from, because you're looking for values that are greater than or equal to 5. So when you go to kind of graph it, you have negative 5 and 5. So you have all these as solutions, and you have all those as solutions when it's greater than or equal to some value, because you can get it from both sides. So this solution would include all values that are less than or equal to 5, and all values, let me use the right notation, the bracket, and then all values that are greater than or equal to 5. Okay, so think about that when you have that inequality sign greater than a number. With absolute value, because it's a distance, you can have it from both sides. What happens when it's less than or equal to? So we can kind of play the same game here. Okay, we know negative 5 will work. So we know negative 5 is less than or equal to 5, but if we go negative 6, then it's going to turn into 6, and it won't be less than or equal to. So we know negative 4, negative 3, negative 2, and we can kind of work our way all the way until we get to 2, 3, 4, and 5, and then we'll have to stop, because once again it'll be less than or equal to. So when you look at a number line on this one, you have all these values from negative 5 to 5 that will be solutions, but once you get outside, so to speak, of those two numbers, they won't work anymore. So from negative 5 to 5 will be your solution. So with a less than sign, you're going in between those two values. So what we end up having is we have, if it's greater than, it represents an or statement. With our compound inequalities, we have two things going on, they're going away from each other. And then we have a less than, which is an and statement. They're going towards each other, and we're looking for the intersection of the two. So this kind of gives you maybe a little bit more than what you needed, but kind of an explanation as to why this stuff works the way it does. So let's go ahead and take a look. Once again, getting back to those steps, though, we always need to isolate. This is one of the biggest things we have to do, because you can't make the determination that we just did until the absolute value is by itself and you're talking about that distance. So you can see if it's an and, it's less than or equal to. If it's or, it's greater than or equal to. We want to set up two cases because we have two potential possibilities. And then once again, we've got to check for this extraneous solution. Sometimes we create these extra solutions when we're solving that will not be true for the original. Alright, so let's go ahead and take a look at the first one. We need to isolate the absolute value. So wherever the absolute value bars are, alright, this needs to be by itself. Not the x, but the absolute value. So you can see that there's a 3 on the outside. So 3 times that quantity means it's not by itself, so we have to isolate it by dividing by 3. So now we're left with the absolute value of 2x plus 5 is equal to 4. Now that it's isolated, we want to set it up into our two cases. I'm just going to call it C1, case 1, is that we know that inside the absolute value, that 2x plus 5 could equal two numbers. It could be negative 4, Or on case 2, 2x plus 5 could equal positive 4. And we're sure that's going to happen because once we solve for x, we're going to get two values that make that inside 4 or negative 4. So go ahead and solve the two linear equations. So x equals negative 9/2 and x equals negative 1/2. And really on this one, if you think about it, we don't need to check it because we have the absolute value set up as a number. So we solved for x so that the inside of that would equal 4 and negative 4, which would always be a solution. So we're not going to get any extraneous solutions on this type of problem when the absolute value is actually equal to a number. So there's our solutions. On the second one, when you look at it, look what the absolute value is equal to. Now it is isolated. This is by itself. There's nothing else with this. There's nothing on the outside of it. But look what it's equal to. And the problem on this one is there's a variable on this side. So we don't know if it's equal to a positive number. We don't know if it's equal to a negative. It all depends on what x is. So this is an example where we are going to have to check for extraneous solutions because we don't know what the absolute value is actually equal to. So case 1, we're going to set it up the same way. Case 1, we know that x plus 15 could equal, alright, I'll just kind of stick to the same thing I did on the other one, the opposite of 2x minus 21. Whereas case 2, and this is why we're going to have to check because we don't really know what the opposite of 2x minus 21 is. Case 2, x plus 15 could equal 2x minus 21. And if those two things are equivalent, then once again, we have to check, but it will give us a possible solution. So go ahead and solve these two linear equations again. So I'm adding 2x and subtracting 15. So I got x equals 2. I'm going to subtract 2x and subtract 15, so negative x equals negative 36, which gives me x equals 36. So these are two possible solutions. We're not sure because we don't know if that, when we plug in for x, if that's going to give us a negative, and we know absolute value can't equal a negative. So we have to check to see if x equals 2 is a solution. So we have the absolute value of 2 plus 15 needs to be equivalent to 2 times 2 minus 21. So the absolute value of 17 is 17. 4 minus 21 is negative 17. So you can see on this example that they are not equivalent. They're close, you know, positive, negative, but definitely not the same. So x equals 2 is not going to work. Let's go ahead and plug in 36. So we're checking to see if x equals 36 is going to be a solution. And we'll do the same thing. We're just going to plug in 36 into our original equation. So we will get the absolute value of 51, which is 51. 2 times 36 is 72. 72 minus 21 would be 52, so 51. So there we go, it works. So our only answer on this one is x equals 36. Man, that was not a good bracket. And so that's our only solution. So once again, going back, realizing that we get these extraneous solutions, sometimes we've got to make sure we go and check our solutions. And you know, when we're solving these different equations that we have, make sure you guys are checking your solutions. All of them need to be checked in some way or another. Alright, let's move on to inequalities. On this one we have we have the absolute value of 4 times the absolute value of 2x minus 3 is less than 28. So once again we have to isolate. The 4 is causing a little bit of an issue, but we can fix that. If we ever multiply or divide by a negative, don't forget that we do need to change the inequality sign. In this case, we're okay. So we've isolated it. Go back to our original. Once we isolate it, determine whether it's an and or an or statement. Do not determine whether it's an and or an or until it's isolated, for the reason I just said. If you multiply or divide by a negative, it's going to switch it. So in this case, it doesn't matter, but you do want to make sure you isolate it first. So this is a less than sign, so you're thinking, less than, it's going to be less than 7, but also greater than negative 7. So it's that and statement that we were talking about. And then you go ahead and set up, once again, your two cases. You have two possibilities. The 2x minus 3 could be less than 7. Alright, so numbers, 6, 5, 4, 3, and decimals and everything, but less than 7. But then at some point, numbers less than 7 don't work anymore. So then we also need the second one, that we want values that are also greater than negative 7. And once again, if it's negative 8, then it's going to give us a value of 8, and 8's not less than 7. So that's why we want to switch the inequality here, and the 7 becomes opposite. And to me, I'm trying to get you guys to visualize that what we're trying to say is, and maybe I can kind of write this and I'll erase it, but you want values from negative 7 to 7, okay? And that's that less than. So you want values that are greater than negative 7 and less than 7. And so you're looking for kind of this in between. Now the numbers aren't going to be negative 7 and 7. That's why we have to solve for x. But that's what we're looking for there. So now when we solve, we'll get two possibilities here. Add 3, divide by 2. Add 3, divide by 2, and you're left with two inequalities. Now we want to make sure that what this is saying is that it's in between these two. So I'm going to go ahead and graph it just so we can see the visual, and it is what we think it is. So values less than 5 and values greater than or equal to negative 2. So we want everything that they share in common, and so our solution is all values greater than or equal to greater than negative 2 and less than 5. So here's our answer. And there you go. Alright, let's go ahead and look at the second one now. If you want to pause and try this one on your own, that's not a bad idea. So I'm going to go ahead and get started. We're going to add 7 because we have to once again isolate the absolute value. If I add 7, I'm left with negative 6. Then I can divide by negative 2, so we're left with the absolute value of 3x plus 15. Now we are dividing by negative 2, so the inequality is going to change from less than to greater than, and negative 6 divided by negative 2 is 3. At this point, since the inequality is greater than, we want values that are greater than 3 and values that are less than negative 3. So this is an OR statement. And then that's how we're going to set up our two cases. 3x plus 15. Once again, we want values that are greater than 3. But we also want values that are less than negative 3. And it doesn't matter which one you do first. They're just two different and two inequalities that we want values between 3 and negative 3. And now as you solve, subtract the 15, and x is greater than negative 4. And then on the other side, you subtract 15 and divide by 3, and you get values that are x is less than negative 6. So before we write our solution, let's get the visual. Here's negative 6, here's negative 4. We want values that are greater than negative 4 and less than negative 6, which is what we were kind of expecting. So our answer to this one is all values less than negative 6 or values that are greater than negative 4. And there you go. And so this works really for, any inequality. You're not, some people kind of, do we check our solutions? Well, you're checking your solutions by looking at the visual in terms of the graph and realizing if it's an and or an or statement. Those solutions will always work then. And the last one. So you can see on the first two that we did, they were equal to numbers. What happens when it's equal to a variable? So let's go ahead and find out. We still set it up the same way. This one once again is already isolated, so we have case 1. Now this is a little bit harder because it's not a number anymore, but you still set it up the same way. You still want to say if it's less than Then we know it's an and statement. So with an and statement, we want values to be less than the original and greater than the opposite. So we have 3x minus 3 is going to be less than 4x minus 11, whatever that value is. And then case 2, you want 3x minus 3 to be greater than the opposite of whatever that number is. Okay, look at the less than that we did originally, which is the first one. So when it was less than 7, we wanted values that were less than 7, and then we wanted values that were greater than negative 7. So I did exactly the same thing. I wanted values that were less than 4x minus 11, but then I wanted values that were greater than its opposite. And now we go ahead and solve these two. I'm going to subtract 3x and add 11. So if I add 11, I get 8. If I subtract 3x, I get x. So x is greater than 8. And then on this next one, I'm going to go ahead and distribute first. So that's negative 4x plus 11. If I add the 4x, I get 7x. Add the 3 is 14, and x is greater than 2. Now, what we notice on this one is that, or hopefully what you notice maybe, is that the inequalities are actually going in the same direction. That's not typically our and statements, but there's nothing wrong with that. We definitely need to graph this to see what's going on. So all values that are greater than 8 and all values that are greater than 2. Well, depending on if this is an and or nor statement, depends on what our solutions are. If it's an and statement, it has to satisfy both inequalities. So where on the graph does it satisfy both inequalities? Well, everything that is greater than 8. Alright, that's where it intersects. So our solution are all values, what we just said, greater than 8. And there you go. So there's kind of a, if you want to call it a special case or whatever in terms of absolute value inequalities. But that's why it's important to understand these first two as to, what happens in that second case. If it's, an and statement, something less than the number, you got it less than 7 and greater than negative 7. And if it, switches to greater than 3, then you have something greater than 3 and less than, negative 3 on, I'm talking about, example 3b. So there you go. That's absolute value equations and inequalities.